Okay, welcome back. We're continuing our videos on the introduction to first principles. Last video we looked at the background of how that formula that we've got on this board here came about. We're going to do some examples today to show you how we use the first principles in its algebraic form. So let's write up our equation here. We've got f of x is equal to x squared. So let's now use first principles to be able to calculate this. So the first thing we're going to write here is we're going to write that dy dx is equal to the limit as h approaches 0. And what I'm going to do here is I'm going to replace all my x's with x plus h, because I'm saying here, if I'm looking at this point here, I'm saying, well, this here is a function of x plus h. If I write in this equation here, x plus h is equal to x squared, well, I'm going to substitute all my x's with x plus h. So in this case, we will have we won't write f of x, we'll just write this here, x plus h all squared. And then we minus what the original function was. So minus x squared. And then over the top, we have h. So what we've done here is we've just substituted x plus h for all our y values, and then minus from that the function of what fx is. Well, our next step is, if we can, we expand. Okay, so expand any brackets. So again, we write down here the limit as h approaches 0. Really important that we're writing that. We get x squared plus 2xh plus h squared minus x squared all over h. Now this part is important because it's from this part that we should be able to cancel down what our function is, f of x is, from everything else in that numerator. Well, in this case, this is our first check. So we're going to cancel down. I can cancel this down and I can cancel this down. I have nothing else left in my f of x. So now I can rewrite this as the limit as h approaches 0, 2xh plus h squared over h. Remember, I'm trying to get this equation down to the point where I can get 0, I can replace h with 0, and it doesn't affect everything else. Right now, if I replace h with 0, I'm going to get 0 plus 0 over 0. I'm going to get nothing, which is not correct. So what I do here is I'm going to factorize h out, okay, only for the numerator. So therefore I'll get the limit as h approaches 0, h 2x plus h all over h. What this allows me to do now is it allows me to cancel out my h's. So now I can cancel h, so I can cancel and I cancel. And now I can write here. I'm no longer going to write as the limit approaches h equals 0. What I'm going to do in this point here is I'm going to say this. This is equal to 2x plus h, and then I'm going to write here as h cannot equal 0. So we're basically saying let 0, or I'm going to put here as approaches 0, has to approaches 0. So I replace h with 0, I'm just left with my derivative function. So in this case here, dy dx, so I'm replacing this with 0, so it no longer exists, is 2x. And this here is the derivative or the gradient function of our original function up here. So x squared, the gradient of that is 2x. Let's do a second example so that way you can see how it goes. So this one here is going to be a little bit longer, so I'm going to start it over here because I'm going to need lots of writing for this one, or lots of space anyway. So, yeah, right, let's do it over here. Let's see. Can I? no, we'll do it up here. I'll be right. So we got f of x is equal to, what have I got? X squared minus 3x plus 5. All right, so here's our function. Let's put it into the form that's asking us to do. So therefore we will write dy dx is equal to the limit as h approaches 0. So we're going to have x plus h squared minus 3x plus h plus 5. So I've replaced all my x's with x plus h. The next part is I'm going to subtract, but I'm going to put brackets around this because I want to subtract this entire function. So x squared minus 3x plus 5. And this is all over h. Now the reason why I put a subtraction here is because over here I'm subtracting the entire function. If I just put minus and not put my brackets here, then I'm just minusing this part, and these signs here are not going to be able to help me cancel down, which we're going to see in a second. So we've written up our statement. The next part is we're going to expand. So let's rewrite dy dx as the limit approaches 0. So let's expand this. X squared plus 2xh plus h squared minus 3x minus 3h plus 5. Now if I expand this bracket here, I get minus x squared plus 3x minus 5. And this here is all over h. So what we have here is our first checkpoint. We now want to be able to see if we can cancel out all of our f of x from the left-hand side. Well, negative 5, positive 5. Positive 3x, minus 3x. Minus x squared, positive x squared. Because I've been able to cancel all this down, I know I have fulfilled that first checkpoint. So let's write the next line down. dy dx is equal to the limit as h approaches 0. We have 2xh plus h squared minus 3h all over h. Now, remember at this point here, we want to get down to making h equals 0, but I can't do this here because if I do, I'm going to get 0 on 0. So remember we factorize h. So the limit as h approaches 0, we get h 2x plus h minus 3 all over h. I now can cancel down, and once I've cancelled down, my next line is going to be, well, dy dx is equal to 2x minus 3, as h is now going to be 0. So we then have our final answer. So as h is 0, we'll write that here, and dy dx is this. So this is our gradient. We started off with this, we end up with this. Now if it said to us, find the particular, so this here is a general part, this here is the instantaneous rate of change. But if it was asking us to find a position or a particular rate of change, an instantaneous, we're just going to substitute this 2 value in. So in this case here, and this here I should rewrite actually as f of x. So f of x, because that's the same meaning but a different notation. So if I substituted 2 into this, I would get 2 minus 3, so I get 4. The answer, or the gradient, when x equals 2, is 1. And that's what it's basically saying. What is the gradient at an exact point on that curve? Alright, I'll see you in that next video. We're going to do one last example. See you then.